Complement the presentation of my colleague Andre this morning from NPL around safety of autonomy. So, Lloyd's Register is one of the partners in the Maritime Autonomy Assurance Testbed, and today we're going to talk about changes in the concepts or the principles of safe flights. So the challenge, I guess the challenge is really very obvious to most people working in autonomy or any advanced software applications. The challenge is really a lot of our requirements, a lot of our processes, a lot of our methods today are very relevant for hardware. And when I mean hardware, these are the electrical, mechanical, and structural elements of the ships. And for example, Lloyd's Register, we've got a lot of standards around this. We've got thousands and thousands of pages on what all of this hardware should be doing, but also what they should not be doing. When you translate that to software, including AI, the challenge is really immense because, of course, unlike hardware, software is not made up of standard components, right? You're really, the limitation of software is really the imagination and creativity of the people developing it. But also when I say standard components, like it doesn't matter what kind of electrical, mechanical, or structural component, they're going to be made up of very similar things like bearings, gears, and that. So really, design definition becomes a very important challenge when it comes to advanced software systems. So this is just a picture, that we've developed to represent this challenge. So what you see on the left is really the growing, or it's kind of like a complexity map where a lot of the assets, even the biggest, most expensive assets in the world that we've dealt with, they're not simple, but they're not complex. They're really complicated, meaning they're made up of a lot of different electrical, mechanical, structural, and software components. But each one of these really there's a defined set of technical requirements. But there's also a method that Lloyd has developed throughout the decades to prove that these requirements are correctly implemented. When it comes to the different systems and autonomy, these are the characteristics on the right. So. The first, important difference is that all the functions, all the performance that are going to be delivered, now there's a requirement for real time, right? So, for example, you would be familiar with machine learning used for computer vision. It's a detection and classification. If it's detection and classification of, let's say, cats and dogs, or pictures of cats and dogs and differentiation, doing that in real time does not matter. But if that same computer vision is installed within the software stack of, let's say, autonomous navigation for cars, it might have correct functions, but if they're not doing it within, milliseconds, it might as well not do the functions, to deliver those functions. So that's a big difference. And of course, slightly outside of that topic, all of this software, all of this AI are ultimately going to be integrated into physical systems, electrical, mechanical systems, of which there's an increasing diversity and increasing complexity as well, driven by the industry. So, and there's a few other things here. One of the things that really increases the complexity is the tight coupling of all this different software and AI applications, meaning a problem in one directly or sometimes indirectly affects other software that belongs to other systems, right? And of course, we care all about these things just because we want to make sure that they don't fail, they don't end up in a catastrophic failure or accident. So those failures are kept to a minimum. So what do we mean by safe by design today? So safe by design today, we've been working with commercial maritime, offshore, and Navy. It just means really doing a lot of safety types and risk assessments, right? So you see some different examples there. Of course, all of these methods, right? I'm not going to go through all of them. The more conventional methods like hazard identification, hazard operability study, fault tree analysis, they remain valid, right? But where the big change is really is this, when it comes to software-intensive systems, defining what all of this software should do on a normal day becomes a challenge. And if you can't define this, you can't define this perfectly, but if you don't have this good baseline, it would be difficult to use some of these techniques, right? If I'm not 100% sure about this function being used under this operating conditions, if I miss that function, there's no way I'm gonna apply any of the safety techniques on that function that has been missed. So what we're saying here is really an extension of that principle of safe by design. You cannot take the functions, the capabilities for granted, but you really need to put a lot of effort in defining them in the first place. So, initially when we're going around to different conferences, this statement has really become controversial when we say that not doing enough design definition, not doing enough requirements engineering can really lead to, not just like some issues, but sometimes it can really derail a project or a program. And again, the intuitive explanation is that if you don't understand exactly what your client wants or what your client needs, and you just carry on, writing lines and lines of software code or integrating different software and AI applications, at the end, they will still have these needs, and if they're not implemented or reflected correctly, they might refuse, the system, right? So, the longer this, let's say, the design life cycle, the longer these issues are not identified or are not taken care of, the more problematic they are going to be in the end. So, again, when we say maritime autonomous surface ship, we're not just talking about navigation. Navigation is an important system in these vessels, but you've got propulsion, you've got steering, you've got a lot of other systems supporting propulsion and steering. And if you think about the entire vessel as let's say as different tiers of control loops, let's say navigation sits on top of them, but the decision is that these navigation systems are going to make, if they can't execute it well because there's a problem with the cooling, so there's a problem with the cooling, it can't supply, or the engine can't generate the right power to do this maneuver, these things become a problem. So it's really important to, navigation system is important, knowing what the ship should do under different, let's say, call regs or collision regulations in ours is important, but you gotta worry about controllability or the effectiveness and safety of controllability at different levels in a vessel. So assurance, why is this an enabler of safe design? We take it for granted. I myself have nearly have 20 years of experience working with Lloyd's Register, and I've been involved in a lot of our teams, going through, working in different countries as well. So we carry out around 30 to 40 unique testing and evaluation activities across different design cycles of electrical, mechanical, and structural elements in the ship. So if really software, there's I believe it's Horowitz Anderson company who said that software has eaten the world back in 2012. So if software is really going to be taking over not just the functionality, but if these systems are going to be dependent on the correct, effective software, then we got to start defining what this assurance means, not just on a software level, but the different design, development, integration activities involved in each software, but also, there's no software that exists by itself, right? There's normally multiple software applications, including AI. And as I've said earlier on, at the end of the day, when you're talking about ships, they definitely end up in electrical and mechanical systems. 5 minutes. So, but also assurance carries out through the life cycle, right? So this is not just like, really testing and evaluation or verification and validation, which is important. But who among here have heard of this concept called AI drift? Or yes. So, and this is the reality of the day, right? Where all of this software, all of this AI applications, in some ways, they're really trying to emulate real intelligence, not just the intelligence of the captain on the ship, but as I've said, give or take, on a commercial ship, there's like 20 to 30 different crew roles, and each one of them do a lot of analyses, decision-making tasks on a day-to-day basis. So, these different AI and software applications are emulating this, and really right now, because of what we see as one of the key issues, there's poor design definition. It's really hard to tell what they can do and what they cannot do. So we see assurance as really not just part of the design life cycle as we're doing with hardware today. We see this throughout the operational life cycle of these different systems, right? Meaning, there will always be limitations, and as if we can identify that, or some of the capabilities that we've proven during design and development, but also testing and evaluation, we might find out that there's like an operational scenario in the field that actually didn't quite work as well. So, proving the different software AI and systems during design is as important as being able to really monitor their real performance in the field and reflecting all those learnings back in the design. So, unfortunately, I don't have a lot of time, and my colleague really packed this slide deck, but I'm happy to answer any questions you may have. So, evidence, right? So, like as I've said, we easily on a complex asset, we have around 10,000 technical requirements on electrical, mechanical, and structural elements of that asset. So in terms of evidence, it's really simple. We expect each and every one of these requirements to be met at different stages of design and development. Sometimes for each requirement, we might be proving them 10, 20 times in these different stages of evaluation. So evidence is very important, but I don't know about you, but anybody who's been involved with software testing knows you're not doing a good enough job if you're not finding some of these errors or defects, right? And quite frankly, some of these errors and defects are so expensive to fix that you're gonna have to come up with justification on how it's gonna be mitigated operationally, right? So that's the reality, and that's the big difference today. When it comes to hardware, our philosophy is either you meet it or not, and if you don't meet it, you do redesign or you do a reassembly. But with software, the nature of the evidence or the results coming from test and evaluation, it's not like a clear pass and fail. Luckily, we've got partners actually. John here from University of York has been developing frameworks to really, organize all of this evidence and say, this is the reason why it's acceptable or safe enough for deployment to the field. Again, I'm not going to go through the detail of. So we believe these little boxes that you see on the right here are really different testing environments. The testing methods are not there, but they're generally applicable to the software development lifecycle, be it you're doing conventional AI or what people call knowledge-based AI, but also if you're doing kind of like machine learning type of or data-driven type of algorithms, right? 1 minute. So, what we're really trying to do, or what we're trying to help the industry succeed here, is I'm not today. We take for granted, but we're buying products that have been really proven, right? It doesn't matter how trivial the product is, right? But you'd see this European working, the maritime industry. You've got actually different types of certification when it's coming from Lloyd's, but with others. But this really facilitates commercialization, but also a level playing field, meaning it puts some discipline or restriction in the developers from claiming too much, but whatever they're claiming credit for and what their product or their system delivers, this is really backed by a lot of evidence. So this is what makes, let's say, like the method of commercialization and scale happen today. So we're hoping to do this by working with the industry, and delivering Matt to be able to enable this to develop all of these different autonomous assets. Thank you.